which you have received. So we're going to start with a very brief introduction about the ACME project and what kind of tutorials it is offering and what's going to happen over the next few months. Then Alexandra is going to present an overview of the AresGW code, more or less how it is working, the basic structure, the main results one can achieve with this. And she will also then discuss the gravitational wave data available by the LIGO-Virgo-Kagra collaboration and basically explain how PyCBC can be used to analyze such data, perform whitening, which is required for the training of the code. Then I will discuss about the basic setup of AresGW, what kind of conda environments you need to set up in order to be able to compile it, and not compile it, to actually to run it, because it's a PyTorch code. And I will also discuss how to construct your own training data, starting from some examples that we also provide here. There will be a break, a half an hour break in between. And the second part will be then to actually run the code, perform training. We have prepared a short data file which allows us to train a minimal version of the code within some minutes, roughly 12 minutes if I remember. And then to evaluate and test it will only take a few minutes. Of course, in reality, on large data sets, this translates to about 2 days of training and some hours of testing. But here, for the purpose of this training session, we have created just a minimal version. And then you can work on the large data set yourself after the session. So this is the plan for today's training session. And of course, questions and comments are always welcome. You can send questions to the chat here in Zoom, but also raise your hand in case you want to ask something before the speaker continues. So I don't know if you want to ask something before we start with the program. Okay, I don't see some comment at the moment, so let's start then. Some small introduction about ACME. ACME is a European project that has been funded to run for 4 years. It started last year. It has includes many different initiatives. For example, to allow researchers to travel to certain laboratories or large infrastructures in order to use them for their research. And also it organizes very frequently different training sessions. So the upcoming training sessions are found here in this calendar. So today we have AresGW. Next week there will be a training session on Bilby for doing Bayesian inference with the gravitational wave data, and then many other training sessions will follow. Also, schools are organized, and also one can gain access to infrastructure as is being advertised here on the main page. Now, ACME is organized in the form of several centers of expertise. And here in Thessaloniki, we are part of the Gravitational Waves center of expertise. This includes ANFN in Italy, the Gran Sasso Science Institute, EGO, and the L2IT Institute in Toulouse. So specifically, here in Thessaloniki, we provide training for several codes. There was already a training session on ERIN, which is an advanced MCMC sampler. This was presented by Nikos Karnesis and Argyro Sasli at the end of last year. Today, we're going to discuss AresGW, and then there will be another training session by Nikos Karnesis using one of his own codes for estimating the confusion noise signal from gravitational waves from galactic binaries for LISA. And in May, there will be another training session where Grigoris Papigiotis and myself will present the rotating neutron star code, the RNS code that has been used extensively by a large number of groups for constructing rotating neutron stars, and universal relations for rotating neutron stars, especially how one can use machine learning to construct such universal relations.
Again, hello from me as well. And now we will discuss about AresGW, and we will see an overview. But first of all, we need to discuss about gravitational waves, and more specifically about the different representations of gravitational waves that we have, with the first being the strain time series, which basically show how gravitational wave strain data progress as a function of time. And in the plot, you can see here basically the whitened data on axis psi and the time on axis x. And you can see the different detectors, Hanford, Livingston, Virgo. And with the darker color, you can see the estimated waveform. Another very commonly used representations are the spectrograms, which are a time frequency representation of the data. And in them, we basically expect to see that banana-like shape, or as we usually call it, the chirp. And the final representation we will discuss is the match filter SNR time series, which basically show how well a template waveform matches the data over time. And we will also see all those representations in the notebook later on, so we will be able to understand a little bit better what we actually see here. But for now, let's stay on here and see that we basically have an unknown word here, match filter. So what is match filtering? Match filtering is a signal processing technique that compares a set of template waveforms, or as we usually call it, a template bank, to noisy data to detect signals with known morphologies. And the basic steps are very easy. First of all, we basically do a Fourier transformation of the data and the template that we want to use. Then we compute the quantity that you can see here, in which the H tilde star is the complex conjugated template and the SNF is the noise power spectral density. And then we can finally compute the optimal SNR by using the formula that you can see in this slide. And we need to do that millions of times because we have millions of templates in that template bank. Okay, but which are the strengths of match filtering? Well, first of all, it is optimal for known signals in Gaussian noise, and that is actually mathematically proven. Secondly, it's easy for us to understand why it works, because it relies on waveform templates, and as I mentioned before, we basically use math. And finally, it is well established. There were decades of development of the gravitational wave template banks, and we have multiple pipelines that use it. Basically, most of the pipelines that are doing gravitational wave detection use this specific technique. However, there are some limitations. of using match filtering, with the first being that is template, that it has template dependence, meaning that it's limited to signals that are similar to those covered by the waveform bank, because it actually checks the match between that waveform and the data. It also assumes Gaussian noise. However, we do know that real detector noise is non-Gaussian and non-stationary. We do have glitches, and that actually reduces its effectiveness. However, those aren't the most important limitations. Now that we expect the new generation of gravitational wave detectors, we will basically have much more data, and that makes the limitation of being computationally expensive a very important limitation. And it is computationally expensive because we basically compare data against millions of templates, and that is very slow and resourcefully and resource intensive, especially for long duration and high mass ratio signals. So that is a problem. And additionally, one more problem that it has is that is limited per detector SNR thresholds. Basically, match filtering runs in each detector separately, and then we do check the coincidence between the two detectors. So for that reason, match filtering often applies fixed SNR threshold in each detector separately. For example, we need to have an SNR from 5.5 and above to consider something a signal before do the coincidence test. And that way we can lose signals that are very loud in one detector but aren't as loud in the other detector. Okay, so is there anything else we can try? Yes, you are here to see AresGW, which is a machine learning code. So, of course, not all hope is lost yet. We can try neural networks since they are everywhere right now. So, what are neural networks? Neural networks are artificially intelligent models that are inspired by biological neurons and their connections that can learn patterns from the data in order to make predictions or make decisions. And here you can see how the most basic part of a neural network looks like. Here you see basically a neuron. The yellow circles are representing the input, and each input is then multiplied by a quantity which is called weight, and that weight basically shows how that input affects the neuron, how important is that specific input for the neuron. Then we add all those multiplications in a sum, as you can see here, and then we add one more quantity which is called bias, which shifts that sum left or right. And that is our final input in a function which is called activation function, and it's a non-linear function that produces the output of that specific neuron. Then we have a lot of neurons that work in parallel that make a layer, and then we have multiple layers that create the architecture of that specific neural network. Okay, and which are the strengths of neural networks? Well, first of all, neural networks can sometimes detect signals that are outside of the training template space because they don't exactly look for a match. They learn how a signal looks like, and they can maybe understand something similar in the data, even though they haven't seen that on the training. Additionally, they can recognize non-Gaussian noise with proper training, meaning that if we train the neural network using a real noise from data, then the neural network might be able to recognize the glitches and have less false alarms. But the most important strengths are those that basically counter the limitation of match filtering, such as neural networks have a real-time detection speed. Once they are trained, the neural networks are orders of magnitude faster than match filtering. And finally, they are also adaptable to multi-detector data, since we can actually train them with multiple detectors at the same time. So they can detect gravitational waves by jointly analyzing multi-detector data without requiring per detector thresholds or coincidence tests. So that way we can detect signals that are consistently weak in all detectors, but they still have a significant SNR as a network. However, we need to be objective. There are also limitations in using neural networks, as with any technique. The first limitation is that we can't understand as easily as we can understand match filtering what is happening. We can't really, it's harder to understand why they make a detection. basically. Additionally, they have a dependency of the training data. We do require large, diverse, and high-quality training sets, because if we have a poor training, we will then have a poor performance. And the final limitation is that they might require retraining for new detector data in order to adjust, but that is not necessary. And now, after that introduction, we can discuss a little bit of history, and we will start our journey by the first machine learning gravitational wave search mock data challenge. For this challenge, there were 4 datasets created, 3 that did contain Gaussian noise with different PSD variations, and 1 that did contain real O3A LIGO noise, cleaned of the GWTC2 events. All the files, I need to mention that all the files that did include 2 groups, 1 for the Hanford detector and 1 for the Livingston detector. And we did have in all datasets the positive samples that were contained, that did contain injections generated by the IMR Phenomex PHM waveform model and real noise, and the negative samples that did contain only noise. Here you can also see the parameters of those injections, and in the plot nearby you can see the individual masses and the duration of those signals for the 4 different datasets. And here you can see the results. The results are presented in a form of a plot of sensitive distance versus the false alarm rate. The sensitive distance, for those that aren't familiar with it, represents the effective range within which a gravitational wave detection algorithm can detect sources at a given false alarm. It is a good metric to use because it accounts for both the detection efficiency and the source distribution. It accounts for the source distribution because we use the chirp mass within the formula that we use to calculate it. And here you can see the results for all 4 datasets. Our predecessor of AresGW Model 1 and 2 code was the Virgo Auth code, which here is represented with a purple line. And in the 4th dataset, that is the most important because it did contain the real noise, you can see that our pipeline achieved the best results out of all the machine learning pipelines. The machine learning pipelines here are represented with the solid lines, while 2 traditional pipelines are represented with the dust lines. You can see here that PyCBC, which we will later use its library, is here depicted with orange. And we have another pipeline that doesn't use much filtering, but wavelets, which is the CWB, which is represented with brown. And here you still see that we may be passing the machine learning pipelines, but you see that PyCBC still surpasses this model in all false alarm rates. So that creates a question. Can we reach traditional algorithms? Spoiler alert, yes we can. And here is where this specific publication comes in place from 2023. And this publication introduces AresGW Model 1, which is the model we will discuss here in this hands-on session. And it is a machine learning gravitational wave detection algorithm for binary black hole mergers. It did include 27 residual blocks and 54 layers in total, leading to 1.3 million learnable parameters. And it also includes innovations such as using a deep adaptive input normalization, or DAIN, a dynamic dataset augmentation, and curriculum learning using an SLR schedule, as you can see in the figure here. Basically, we did start the training by giving the network only signals with higher SNR values because they are easier for the network to see and learn. Then we did proceed by giving signals with lower SNR values, and finally we did provide all the signals for the network to see. We will also discuss the curriculum learning later on when we'll see the arguments of the training. And now that I mentioned training, we need to have an idea of the train test pipeline, what it actually happens. We firstly have the input, which includes Hanford and Livingston DACA stack, one near the other. Then we do perform widening of those time series. And finally, we do the normalization using DAIN. And that is the input that we feed the network. And then the network decides what it thinks about that specific segment by producing an output, a ranking statistic, with values from 0 to 1 initially. That shows how confident the network is that this segment that it looks at that time is actually an event. And we have two phases. We have the training phase and the testing phase. When we do the training, the input are data that used for the learning, and the output is predictions on those training data that actually change the weights of the network. And when we finally end with the training, we have the final results, we have our weights, and now we can use those weights as much time as we want to test unseen data for evaluation and do actual predictions on those unseen data. Okay, so what did we use as a training dataset for that specific pipeline? We did use 12 days with noise with real data quality of O3A from both LIGO detectors. So as you do understand, AresGW is a two-channel network, meaning we have two input channels, one for the Livingston detector and one for the Hanford detector. The waveform model used for the injections was the IMR Phenomex PHM, and the mass range was between 7 solar masses and 50 solar masses for the individual masses. However, even though that is the case for the individual masses, the distribution we end up with for the chirp mass is the one that you can see in the figure here because of the relation, the non-linear relation between the chirp mass and the individual masses. And even though that specific distribution is actually aligning with the real distribution in that specific chirp mass range, it isn't optimal to train a neural network. Neural networks prefer uniform distributions because with distributions like this, they might learn well the signals in the middle parts of the distribution while they tend to ignore or they aren't trained as well in the signals in the outer parts of the distribution. So we can consider the effective training range for that specific network to be between 10 solar masses and 40 solar masses for the chirp mass, which is also the 95% confidence interval. Okay, and which are the results? The result is that AresGW model 1, here represented with blue, surpasses the standard PyCBC in that specific setup, which is basically the dataset 4 of the challenge. However, anytime we do an evaluation in a small dataset, here we have a dataset that has 1 month duration, which is small, we need to also present variance in different test datasets of the same duration. Because as you can see, there might be a variance. Here we see that the variance is actually very small. So we're good. However, that start again creating questions. What about the variance? We need to know how do sensitivity metrics fluctuate due to dataset variability. And this is our latest work, this paper here, Robustness of Sensitivity Evaluations for Gravitational Wave Detection Algorithms. And in that paper, we did use 1 month test dataset in order to be able to test two different metrics, the sensitive distance and the number of detected injections at different false alarm rates. And in order to do that, we did create 28 test sets in total, and we did divide those in 3 categories, each containing 9 different test sets and one common among all the categories, the reference set, which is the same as dataset 4 from the challenge. What I also need to point out here is that because, as I mentioned before, only the event from the GWTC2 catalogs were removed from those data because we did use the same files as those from the challenge, there were still 37 gravitational wave events from the AresGW, GWTC 2.1, EAS, and OGC catalogs present in those data. And those affect the data, as we will see later on. Now, the 3 different categories we ended up with were datasets with identical noise and varying injection compared to the reference dataset. We have datasets that had varying noise and identical injections. When we say identical, we mean the parameters. We had identical parameters. However, because we inject in different GPS times, we do have a different projection and detector patterns. And the final category included datasets with both varying noise and injections. And here are the results. We did notice that the sensitive distance at false alarm equal to 1 per month is robust at a signal 1 month evaluations. However, that is not the case for the number of detected injections, as it shows high variance when we use a single 1 month evaluation. And you can see that here in the figure that for false alarm equal to 1 per month, we have a very different performance amongst the different datasets. We can say that the number of detected injection is robust, but when we reach a false alarm rate equal to 100 per month, which is actually too high for a credible detection. Additionally, we did see that including real gravitational wave events in the noise actually biases the number of detected injections, but it doesn't affect the sensitive distance. And finally, we did conclude that in order to have a robust evaluation, that would require from us to have multiple datasets, real event removal, uncertainty reporting, diverse metrics, and standardized protocols for the community. And then we reach the critical test, which is the performance or real data. Here you see the publication for the latest model of RCW, RCW model 2. The new enhancements of that model included that we had, first of all, a larger training dataset. The duration of that training was 35 days compared to the 12 days that we do have for model 1. We also did use double precision floating point format, but only on the final softmax layer and only for the data analysis. And then we ended up deciding that we needed to use a different ranking statistic than the initial output of the network, because we did see that a lot of the events were actually all concentrating to the rank statistic equal to 1. And we couldn't really see the results that way. So we decided to use a logarithmic ranking statistic, as you can see, by using the formula that we have here, which is the initial output of the network in the range between 0 and 1. And the added value is to avoid problems with the logarithm. And one more enhancement was the use of a 350 Hz low-pass filter in both the training and the data analysis. And we did use that in order to be able to clean the high-frequency noise. And you can see how that looks here. We have the same segment, but with different bandpass, and you can see the difference. The data analysis methods that were used were, first of all, glitch removal using the Gravity Spy, which is a machine learning pipeline that detects glitches. And we did use that for both the background generation and the analysis of O3 data. We also did perform a hierarchical classification of the triggers using different filters, and we ended up with 3 categories: the default low pass class, the selective noise rejection class, and the selective passband class. And we also did a ranking statistic optimization, because we didn't use the one value of a ranking statistic, but a mean of ranking statistic by basically shifting the start time of the segment we were checking each time. And that way we could take a better representation of the ranking statistic for that specific trigger. Okay, and using all that, we managed to actually detect new candidate events. So because we had new candidate events, we needed to perform the necessary consistency tests, such as checking the arrival time and made sure that it was below 10 milliseconds, because that is the time that a gravitational wave needs to travel from one detector to the other detector. And we also did perform the chi-square test, which also helped in finding the effective SNR, which here is depicted as rho hat. And we also did perform a parameter estimation using the Bayesian inference library Bilby. You can see here a corner plot of one of those events. And here you can finally see those 8 new gravitational wave events. You can see the event name, the GPS time, their astrophysical probability, their false alarm rate, the sample average rank statistic, the mean rank statistic if you want, the time delay between the 2 detectors, the chi-square test for each detector, and the class that they belong. And I won't say much here, only that they have a cumulative astrophysical probability of 5.94, which is very good. And also that all of our 8 new gravitational wave detections were actually subsequently verified by an independent parameter estimation study later on. And here we have the conclusions. Specifically in the paper, we do mention also what RSW detects in the real data besides the new detection, such as it actually achieves in finding 34 out of the 43 events within its effective training range. It also detected 10 out of the 55 events outside of its effective training range. And finally, as we already mentioned, it did detect 8 new gravitational wave events. And you can see here the QP plots of those 8 new events, and you can clearly see the chirp that we expect to see if we have gravitational wave there. And I also present here time series, 2 time series examples, in fact, for those new candidate events, in which you can see the data of the detectors and also the waveform estimated for those events. So this is the overview. If there are any questions, I'm happy to answer. Don't be shy. Now is the time.
So, yeah, I don't see something in the chat. No hand. Or you can speak up. Anyone who wants to ask something about the first presentation? Or should we continue with the second part?
I won't go easy on you, ask. Okay, maybe they want to think about what they heard.
So at any moment, you can interrupt and ask a question. So Alexandra can now continue. We have so now the discussion about the available data that you can download and either use for training or then for trying to detect in the data stream of LVK new events, which is something very exciting.
Yes, it is.
Okay.
Indeed. We still have no question? Do I continue?
Yes.
Okay, so let's discuss about the LVK gravitational wave data. For this analysis, as we did mention earlier on, we will use the PyCBC library, which is a toolkit designed for studying gravitational wave data. This notebook is, you can find this notebook in Git, and you can actually run it as it is because we do install the PyCBC library directly within this notebook, as you can see here. I also need to point out that this notebook is largely based on a combination of the first 3 official PyCBC tutorials, which are available here, so feel free to also check those. Here are some other important imports. And the first thing that we will do is that we will use the catalog of binary mergers. The PyCBC provides us an IP for accessing the public catalog of gravitational wave detection from compact binary mergers. And those, of course, include binary black hole mergers, binary Newton star mergers, and Newton star black hole mergers. And you can finally see them by actually using a catalog point cataloging here. Mind you that this specific step will actually print only some default events that are installed here. However, the catalog part actually include all the events until 03. You will see that later on. We can actually also assess their parameters. We can see the event time, the component masses, the luminosity distance, and the chirp mass. But what we need to keep in mind is that at first, those parameters are found in the source frame. So here you can see that I can actually either print all the catalog chirp masses, for example, or I can print the chirp mass for a specific event, for example, this BNS that I use here. You can see here I use this event which is from 02. However, here in the print, we don't see events from 02. So yes, we can transform the mass parameters into the detector frame by using this simple formula in here to account for the cosmological redshift. And you see that we basically use that formula here, and we can finally see which the source frame was and which the detector frame chirp mass is after that. Here we will use at first this event, which is also the first event ever detected, but I also included here a list of other events that will actually work for this notebook exactly as it is without changing any of other parameters within the notebook. So you can check for yourself and change the parameters to see difference. Now, moving on to actually accessing the LIGO/Virgo data, we will do that by using PyCBC, and basically all the objects that will be returned will be PyCBC time series objects, which actually include built-in methods for filtering, transforming, and analyzing strain data. We can immediately get data from around a specific merger by using the catalog. And in most cases, those data are actually centered on the merger time. However, there might be restrictions, and we maybe need to actually use the full data. We won't do that here, but you maybe need to. Or if you're looking for a new event, for example, you might need to use the full files for that. So now let's inspect the raw LIGO strain data and see. We basically expect, when we see the raw data, that we will have strong low frequency content, which will be visible as large amplitude oscillations. And we might see a DC offset. That's not necessarily, but for this event, for example, we will see that a DC offset. And in general, we will see noise. And here is what you can see. Basically, we have that DC offset in the different detectors. Here we use Hanford and Livingston. If you have an event that also include Virgo, you can include that here by using V1. And now we can also zoom to see what is happening around our event, because here we do use the total 32 seconds around that specific event. And when we zoom, we can actually see the low frequency behavior in the noise, since it's actually much higher than the frequency of the signal. Basically, here we have other oscillations from other frequencies, higher frequencies. Okay, so we need to start the data processing, because that way we can't really see much. And we will start that process by, first of all, using a high-pass filter to the data to remove the low-frequency content. And by doing that, we will actually see here that we removed the DC offset. However, we still have some dominant frequencies here. So we have other process steps to go to. And here is where the power spectral density comes to place. In order to understand how the detector noise varies with the frequency, it is essential to use the power spectral density, which actually quantifies how noise power is distributed across the different frequencies, and that actually plays a central role in match filtering, in calculating the signal to noise ratio, in widening, which is maybe the most important part in order to be able to find a signal, and in general assessing detector sensitivity. Here in this specific notebook, we do calculate the PSD using a version of Welch method, which basically works by dividing the data into overlap segments. Then we do compute the Fourier transformation for each segment, and finally we're averaging the square magnitude. And that way we can finally have the PSD. What we will see when we check the PSD in the full frequency range is that we will have large noise power at low frequencies, mostly because of seismic noise and other environmental disturbances. And we will also see some sharp peaks at specific frequencies, which most are known instrumental features, such as the 660 Hz electrical power line noise. And here is what that actually looks like, as I mentioned. Here, because we cut from a frequency and above, you can't see really the seismic noise magnitude here, but you can clearly see those peaks of the instruments. Okay, so what we do need to do now, we do need to proceed with the whitening. That's why we did compute the PSD. And mathematically, what whitening does is that it divides the data in the frequency domain by the square root of the power spectral density. And after transforming back to the time domain, the noise should fluctuate around zero. The variance should be approximately uniform, and astrophysical signals can now appear as visible executions from zero. From those that aren't familiar with the term whitening, basically what we do is that we transform the strain data so that the noise has an approximate flat PSD. So it rescales the data so that the frequencies are actually contributing more equally. And that is what we do here. And you can actually see a big difference between this plot and the previous plot that we had only with the high-pass filter. So you can also actually see the signal. The signal is in here, but in order to be able to visualize the signal better, we would need to actually band pass after whitening and use the frequencies that are actually proper for that specific merger that we're checking. For example, for this specific signal, the GW150914, using a bandpass with frequencies from 30 to 250 Hz is completely fine. And as you can see, after using that, we can actually very clearly distinguish where the signal is compared to the noise. And we can actually focus the plot around the signal and see how it actually looks like. So these are the two detectors, and you can clearly see the waveform of the signal that is within the data. Now, it would be also good to actually align those two detectors in order to compare the signals across the two detectors, because we do expect coincidence. And here you don't really see coincidence. So first of all, why there is a difference here, why they aren't one on top of the other. We do have a time of flight delay. The wave reaches different sites at different times. As I mentioned before, for the two LIGO detectors, up to 10 milliseconds between those two, maximum. And we also might have a relative sign phase difference response, because depending on the source sky location and the detector's antenna patterns, the strain measured by one detector can appear with approximately sign flip relatively to the other detector. And more generally, we will have a small phase amplitude difference between different detectors. Now, in the official PyCBC tutorial, in this specific part, they actually use immediately the known difference, which is approximately 4 milliseconds for that specific event that we're using, the first event. However, that only is okay for this specific event, and we wanted this notebook to be event agnostic so that you can actually test different events yourself and see different things. So we did decide to estimate the lag and the sign using cross correlation. So we do define a Hebel function here that you won't find in the PyCBC tutorials, which takes a reference train time series, for example, the Livingston data, and have a target time series, which actually can be the other detector, for example, Hanford. Then it normalizes both series. So we have zero mean and unit variance in order to make the correlation scale independent. And then this function computes the cross correlation and searches for the peak with physically plausible lag range equal to 10 milliseconds, which is again the max that we expect for those two detectors. And also by seeing if the correlation is positive or negative, we can actually determine if we have a plus sign or a minus sign. Now, that method can fail if we have, for example, low signal to noise ratio, if we use short data windows, if there are glitches present in that specific segment, and other things. Or, for example, very long signals. However, what I need to point out here is that the correlation-based alignment is not the most physically rigorous way to find the interdetector timing. The fully consistent approach is to actually use the source sky location and the detector geometry in order to predict the arrival time delays. And that would and also account for the full detector response. However, in this hands-on notebook, we do not have a reliable sky localization, and I didn't want to make you actually search to find that number, so you can use that. And this is the function that I just described. Here we also do a passband, and after using that, you can actually see that now they are perfectly aligned. So we can say that there is a gravitational wave event here that appears in both detectors. So you can also go back and see the difference, how it was before and how it is now. And finally, we reach the match filtering part, which also was discussed previously. Match filtering, as I mentioned before, involves sliding a theoretical waveform, which we call template, across the detector data and computing a weighted overlap between the two. And that is exactly what we do here. But in order to do that, for this notebook, we will only use one template. We will generate one waveform. And we will assume, for being easier at that point, equal masses for M1 and M2, which is okay for this specific signal, which is because it is within its posterior probability. And that specific value here is okay for the other signals that I include in the list above. If you want to check other signals beside those, you might need to change this value, or you maybe need to have different mass values or add other parameters here beside the default parameters that are included in the getDD waveform function. Here you can also see the approximant that is used here. There are different approximants. For example, for the injections, we did use another, the IMR Phenom XPHM. There are also details here in what is happening. I won't go into detail because of time constraints, but you can see here, for example, we do have the waveform, but we do a cyclic time shift in order to have the mergers at the start of this segment, and then we basically shift that, and everything that comes from the right ends up on the left. And now that we have the waveform, the template waveform, we can actually calculate the signal to noise ratio time series by just using mass filter, and include here the template that we used, the PSD, of course. We do include a low frequency cutoff, and we also include the whitened real data. Here you can see we are doing some crops near the edges because we don't want to have a problem with the filters that end up having glitches in the outer parts. And by doing that, we can actually see here the signal to noise versus time plot. And you can see that here we found a signal at that specific time with the signal to noise ratio equal to that. Here we only use it for the Hanford detector. Feel free to try the same for the Livingston detector as well. We also want to see now the alignment between the signal and the template. And we very easily do that similarly with before. Now here by using the time that came out from here, or by the same catalog object that do include the arrival time, you can actually align the template with the signal. And we can also do something else. We can also subtract that signal from the data and see what the residual is. if there is a good match between the template and the data, we won't see a big residual. If we have glitches, for example, or if the match isn't as good, we will see a difference. Here we have a very good match, as you saw here. So because we have a very good match, you see here the noise is the same, and here we have the signal, and here is what the residual is after removing the signals. For the other events that I include, you might see that there are residuals here because that specific template that we use isn't the best. For example, we can show an example. Here, let's say that I want this. Can see how it is here and how well they align. But we did wanted to see the difference in this specific one doesn't have one. Let me try another one. Okay, it's stuck. For example, here, you can see the signal is here, and you can see some residual of the signal here and here. Feel free to try it yourself. So that is the notebook. Before moving on to discussing a little bit about the gravitational wave Open Science Center and see how we can use it and what we can see there. Are there any questions? Can you share their questions in the chat? Because I can't see the chat here.
Not in the chat.
Are hands up or something?
So who wants to make one question so that we can continue? What was not very clear? Or what created some additional questions?
You can even ask me my favorite color. I will answer, I promise. I guess I said them all so clear that there aren't any questions. Can you hear me? Let's start from that. Do you hear me?
Okay.
Okay.
That's a good sign. That's a good sign. All right. Okay. Here. Good. There is a question by Stratos.
Okay.
Regarding the training of RSGW, are you currently utilizing generative models for data augmentation? Specifically, could RSGW be trained to generate its own synthetic waveforms to improve its ability to detect signals that might fall outside the current bank of numerical relativity templates? Yeah, very, very good question.
Okay, I'm not familiar with generative models, but the data augmentation is actually happening in a very simple way in AresGW. We basically take a segment and with the probability, let's say 40%, we do change the noise in the other detector from noise nearby, basically. So that is the way that we are doing the data augmentation in RCW. I'm not sure if that is similar to what generative models do. Now for the second part, tend to generate its own synthetic waveforms. I mean, it could, but I'm not sure how that really would work. But the code can be generalized in many directions, the way it is written. So I guess we could, for example, when we do that augmentation and we basically now change only the noise and then we put the injection on top, we might then, when we do the augmentation, include different waveforms there, for example, those synthetic waveforms that you mentioned, in order to be able to get trained in different variations, for example, of general relativity, let's say. That could happen. That could work. Sure. I hope that answers your question. I don't know if Professor Stergioulas has something to answer to say more here.
Yeah, so at the moment in RSGW, we are using known waveforms that are produced by specific waveform models, but other approaches include a more agnostic approach where you generate wave-like disturbances. For example, using a wavelet basis and train a neural network on that larger possible space of such wave-like disturbances, in the hope that you will detect something, a real signal that might fall outside your known wavelet, training banks. Okay, this one can attempt. We have not done this ourselves, but I can imagine that while on one hand, this may enable you to detect modified gravity waveforms, if such exist, for example, it also may produce a higher number of false alarm rates. So these generalized wave-like features that you will use as training data may adapt well to glitches, and so you may get many triggers that actually correspond to glitches and not to some real astrophysical signal. So there is a trade-off here. How much you want to depart from known waveforms where you have some knowledge and an ability to judge whether this can be astrophysical or not, and how much you are able to risk to have a higher false alarm rate, which then will cast doubt on any trigger that you will find. So these are things that we need to experiment more in the next couple of years to arrive at some safe conclusion. What can we really use and what is meaningful to do?
Yes.
So, yeah.
Also, I think that question maybe relate more to the new detector data that we will have with the new detectors, because with the data that we have now, I don't think that a difference in general relativity, a small difference in general relativity, would be visible in those data enough to create something very different. So I don't think that there would be something really important there to find. We would find basically the same signal, but maybe with a little bit higher ranking statistic. But I can't imagine finding something completely new, except if we have a completely different waveform to begin with.
Yeah.
Not a small variation in the one that we have right now.
Right. Yeah, I agree. Yeah. But in the near future, in 2 years from now, or maybe a bit more, there will be the next observing run, which will have higher sensitivity, and then another will follow. So every time we will have better and better sensitivity, more and more astrophysical signals. So this will become relevant. And so here is a comment by Lazaros, who says that in the future we could use generative models to generate a higher variety of glitches for better and more reliable noise classification. Yeah, I agree with this. So we should work on both fronts to, on one hand, have better models for the astrophysical signal. On the other hand, have better models for the glitches in order to separate clearly these two classes of triggers.
I partly agree, partly disagree, because there are glitches that have a very specific form, so you do need to train on them. But for smaller glitches that don't have a specific form, sure.
Yes, yes, yeah. So of course, the glitches some of them we know very well, so there are clear models, but others it would be good to probably create a variety of them. And yeah. Okay, more work for the future. So, but for the moment, let's see now what kind of data the Open Science Center provides to us.
What you can basically find if you search a little bit in the gravitational wave Open Science Center. So basically, this is the first thing that you will see when you click on the page. And we won't try to see everything here because there are a lot of things to find. But the most important is that you can actually explore the data here, and you can find the events and the catalogs that those events belong. You can find the different data releases from all the periods that are publicly available so far. For example, O4A, you can see O43B, O3B, O3A, etc. And you can download those files and work directly with the complete files of each period. But they are pretty big because we talk about periods of some months or maybe year. So yes, keep that in mind if you try to download them from here. Now, going here, we can actually, again, go to the events and catalogs. And if we click on the events, we will actually see the event list. And here you can find all the events that are, again, in the publicly available data so far. So for example, you can see here also events from the recent publications for which the data might not be available yet. However, all those events are here, and if you go down and here you press show all, you will find all the events. You will also sometimes see the same events multiple times in that list because we have the same event in different catalogs, or we might have something that seems like an event, but then it got dropped. So it will say here, for example, auxiliary for that specific case. Now, for each event here, you can clearly see the version. You can see the release catalog, the GPS time, the individual masses, the network SNR, the distance, the He effective, and the total mass. And you can actually display also some other parameters. You can find those parameters here. You can see the chirp mass, the detector frame, chirp mass redshift, false alarm, astrophysical probability, and final mass after the merger. Additionally, if you go to one of those events, for example, say, I want one of the previous events because for the new events, there are additional things here because there are different tests. So, for example, if we go here, we will, if you press in at any event, for example, you will see which detectors did detect that event. For example, here we see that all three detectors did run that specific time. So we have the spectrograms for each of those detectors, and you can here again download the data for that specific event in different sample rates, for example, and in different forms, for example, HDF, TXT, etc. Additionally, here you will see the event name, the release, the GPS time. You will see also the same time as UTC time here. And by see that, you can actually see why that specific event did take that name. So it was detected on 2020, the second month, at the second day, at that specific time. That is how we do name our events. You can also find the pipelines that did detect that specific event. For example, here only GST-LAL and PyCBC binary black hole search pipeline did find that event, did see something. That specific event was detected with an astrophysical probability greater than 0.99 for that specific pipeline. And what happened with PyCBC? For PyCBC, it is the same. Sometimes you might see here pipelines that did see the event, but with astrophysical probability lower than 0.5, which basically means that they don't consider that an event. Those pipelines don't consider that an event. You also see the match filter SNR, the network for all three detectors, and the false alarm rate. And you can also find the parameter estimation here. You can also download the parameter estimation files from here. So, for example, you can look for the sky localization if you want accurate values to use here, for example. I just say an idea. You can do whatever you want with that. And if we press here, we can actually see more parameters that we did so on the previous table. We can see the He effective, final spin, luminosity distance, redshift, sky area, etc. And you can also see the confidence interval here. Now, we do see that here, and I did mention that we have this GPS which correspond to this specific UTC time, and that is where an event take its name. So if you, for example, want to use SW in order to find new events, like we did, how would you know how to name them? Well, you can go to the timelines here, and here, if you select a different observing period, you will see the GPS start and end times changing. So if you want to know how which was the duration for O4A, for example, you can just press here and you will see that it started in that specific GPS time and it ended in that specific GPS time. This is the UTC time and this is the duration. And if you want to find a specific event where it did happen, you can go, for example, here and take one time. Let's say I want this one. And you can go here and just insert that here. And if I press enter, that will give me the UTC time of that event. And let's see if we actually did what it needed to be done, if it's correct, the name. So we do see that it was detected the 2025, the first month, the 14th day, and on time 082203. And this is the name of the event. I won't say anything else here. You can try and discover things for yourself. There are tutorials, there are workshops, software, there are different things you can check, but that's all from me. If you have any questions, please don't be shy.
Okay, so
I think that now it's the time for Professor Stergioulas to come back.
Okay, if there are no questions at the moment, we can move on to the next item in the timetable. So let's switch
microphones.
All right. So let me share my screen now. All right. So we are here to discuss about the setup of AresGW and the training data. Information about this is contained at the repository that we have linked to the timetable. I hope you all have already checked that you have access to this. Is this correct? Everyone can access this specific repository. So it will lead you to this GitLab repository. One thing I should note is that because we provide sample data for noise, otherwise you would need to wait for more than 2 hours to download the full noise file that is available through the first machine learning challenge. As I will explain, we have provided, and the full file is something like close to 90 gigabytes. So I guess it is not practical to use that at the moment. So we provide a smaller one that is about 500 megabytes of size. But this means that in order to get it, when you clone the repository, you need to have LFS enabled in your system. So, and if you don't, we provide here some instructions how to do it. All right, so we start then with the README file of this repository and go through the steps here. In order to set up, we will use two different Conda environments. One which has fewer modules loaded, and it's sufficient to generate the data. And then we will switch to another one that requires many more modules to be loaded, and that is for the actual training of AresGW on a GPU card. But let's start with a simpler one that is sufficient to generate data. And for this, you need to create a environment in your Linux or Mac system. I assume there is a way to do this also in Windows, but I'm not using it. So if you're using Windows, I leave it up to you to figure out how to do this. An easy way to set up such an environment is to use Miniconda. So you don't need to install the full Anaconda distribution, which is very large. Miniconda is sufficient. There is a link with instructions here if you don't have it already. Once you have it, then you can simply issue the command conda and create this environment, where the specifications for this environment are contained in this file that we provide here. And it just tells the conda which packages to download and create a specific environment to run our codes in there. So you need, for example, a recent version of Python, you need PyCBC, you need LIGO segments, then you need the HDF5 library, because this is the format that we use for data, and some pandas for then using some notebooks to inspect the data. So nothing more sophisticated than that. So why don't we try? First of all, I assume that most of you are familiar with cloning such repositories, but maybe not everyone. And so why don't we do this first? Here, this I don't need. Okay, here I have a terminal. Okay, where in this terminal now I can clone this repository using git clone. Okay, so this is supposed to be a hands-on session, so we're going to do all the steps manually so that you can see exactly how it works, and you can reproduce them. This repository, because it contains this large 500 megabyte file, takes about 2 minutes to fully download, not more than that. On a good connection, it takes about 2 minutes. Otherwise, it may take somewhat longer, but eventually it will be downloaded. And then what we will see is how to create exactly this first environment that will allow us to run subsequently the different codes. Okay, so maybe another minute and it will be done. Yep, here it is. Okay, in the meantime, there is, no, okay, in the chat, good. All right, so we have our environment. Let's check here. Yeah, it is this one. So we enter our repository, and now we can create this environment. So all we need to do is to issue this command, containf create. In the environments folder, there is this YAML file that has the specifications. Of course, in my case, this environment already exists. So here it will just check the requirements and then it will simply conclude. In your case, it will download these different packages and then create it.
I have a problem.
Yes? Okay.
There is a problem.
Let me check.
We need to make sure that we have the correct access rights.
Wait a moment. Git clone, clone in NT. Well, if you, yes, in this first question, you just answer yes for the fingerprint, if it's the first time you do this. And yeah, could not read from the repository.
Maybe we need to specify that it's not just for reading publicly. Is there something like that? I don't know.
No, it is a public repository.
Yes, but they can see it. Can they download it? Or should we enable something else in order to be able to be downloaded?
This repository, the settings are here. And for the visibility, it's a public repository.
The visibility for additional things?
What things? Here,
They can't download it.
yeah, that is the visibility, that how to be allowed to download it. Can someone else try this and let us know?
Excuse me, but
if you can actually
Constantina, you had Git
download this repository,
Git, I guess.
to clone it actually. Okay, great.
Perfect.
Great. All right. So we have created our environment, and now we need to activate it. So with conda activate, we now work in this environment, and here you can see it also in the command line. All right. All right. Next step is to generate data, and basically we will start with a noise file because we want to train AresGW, and so we need to allow it to recognize either the noise or gravitational wave injections. So we start with a noise file. In this noise file, we will then, in half of the noise segments, we will inject gravitational waves in order to have both kind of training data segments. Here in the repository, in the README, you can see the command that allows you to download a very large noise file with size around 90 gigabytes. That this corresponds to about 80 days of noise. That is sufficient for training for a production run AresGW. But as I mentioned before, we don't want to do this right now. It will take more than 2 hours. So instead of running this command, what we have done is we have created a Python script that takes this large data file and creates a subset of this. So in this way, we have created a smaller file that instead of 82 days, it has a duration of only 10 hours of noise. 10 hours is sufficient to create a minimal example for demonstration here. Okay, so right now we don't need to issue these commands because this is already done, and this file is provided in the directory here in general data. You can see it's this file, and with LFS enabled, you can download it. Okay, so we go then to the next steps, which is here. There is a script called generate data that will now perform the injections of random waveforms within some specifications into this noise file. We will then, once we do this, we will go through some notebooks with which we can inspect both the noise files and the injections that we have introduced in the noise. So let's do this. In fact, we will need to do this 3 times because for training AresGW, you need a training dataset, you need a validation dataset that will be used during training to evaluate the accuracy of training. And then in the end, you need an independent test set where you can evaluate afterwards the false positives, the false alarm rate, and create different sensitivity metrics. So we need to run this 3 times. All these 3 must be independent. So here we provide another script, generate all sets.py, that basically calls generate data.py 3 times and creates with one run, it creates all required files. So let's do this here now. Okay. Yeah, of course. I need to go into the directory generate data. So once I'm in generate data, I can run this script. It loads the shorter noise file that I specified here. And then you see that it is looking at the injections. In reality, the injections are a very large number of more than 500,000, close to 600,000 possible injections, because the different parameters that determine a waveform, especially when you have free spins, it's a high number of parameters. You need a large number of possible waveforms to cover it well. But of these nearly 600,000 injections, only a very small subset will be used for this shorter noise file that we have. Only a few hundred in the end. So our minimal example for today will start with a few hundred random waveforms. But of course, later you will be able to use the full file. So this will run 3 times. Okay. And while it is running, we can start looking at the different notebooks to see how these files look like. So the first notebook we are going to go through is this inspect data file. Okay, there is a link here in the README. So now we're going to look at this notebook. And actually, we're going to inspect the full 82 days noise file, not the one that we are creating right now and injecting there, the smaller one. We're going to inspect the full file. And this is actually data file. Okay. So I have stored it locally under this name. Here you can change the name of the file and inspect any other you create later. So in this Python notebook, we import the necessary libraries. Maybe I will enlarge a bit. Okay, this looks better. We specify the file name, and then we open it. Since it is in HDF5 format, there is a special command in this H5Py library that allows us to open such binary files. And such files have a very specific structure. There is a root level with specific groups. And here we can list the keys for these groups. We see H1 and L1. This means that at the highest level, this data file is structured so that first you have all the data from the Hanford LIGO detector, followed by a second group with all the data from the Livingston detector. In the repository of the first mock data challenge for gravitational waves detection codes, for machine learning codes, that we provide a link in the timetable to this, you will find a schematic of the structure of these data files. So there is the root level. Here you see the 2 groups, the one for the Hanford detector, the one for the Livingston detector. And then in each group, there are data segments specified by their length. 7,200 is in seconds. When these files were created, there was a minimal length of 7,200 seconds specified. And each such data segment also has two attributes, which are the start time and the time step, delta t. Okay, all of this we can see here. So here in this tutorial, we provide the necessary Python routines to read the file and print exactly the structure. So we have the group H1. The first dataset starts at this GPS time. This is the length of the data. It has two attributes, delta t. This is the time step. This corresponds to a sampling rate of 2 kilohertz. Okay. If you want to study the gravitational wave emission from, let's say, post-merger phase of binary neutron star merger, you would need to increase the sampling rate to at least 8 kilohertz. But here, for binary black hole mergers, for the inspiler phase, and specifically for the mass range that we are using, 2 kilohertz is sufficient to allow us to work with such waveforms. Then there is a second data set at this GPS time, a third one, a fourth one, and so on. And we see that in total there are 4 plus 3, 58, so there are 362 data sets included for Hanford, and the same number for Livingston. So you may ask, why is the data split into so many different data sets? Why isn't it a single continuous data set? I think very soon you will see the reason in a very interesting plot that we are going to generate. But before that, let's create an informative table by using this data. So here, this is another function that we provide here, with which you can make a nice plot of this table for both detectors. So IFO is the interferometer. Here it starts printing the datasets for Hanford. The segment key is the name of the segment that corresponds to the GPS start time. This is the actual start time then, and in GPS time. So you see that this is just derived, the name is derived from the actual start time. Delta t, then the number of samples contained and the total duration. If you multiply delta t by the number of samples minus 1, then you get the total duration. So we see here that the first dataset has a duration of around 10,000 seconds, the other one 11,000 seconds, 8,900. Here we have a dataset of 30,000 seconds, and so on. Since we specified a minimum duration of 7,200, all of these are larger than that. Otherwise, we could have created datasets of smaller duration. Okay, so and now it will become apparent what is happening. So here we provide additional routines to actually read the whole file and plot the data coverage. So these blue lines here are showing you exactly where you have data. On the horizontal axis, we have the GPS time since the start of the data file. In total, it's more than 175 days, maybe close to 180 days, which this is the calendar time, let's say. And here, this first thin line is actually the first data set that you see here. Then the additional lines, each such data set with its own duration forms an additional line here. And depending on duration, you see different thickness. Like here, we have a very long duration data set. So you realize that the data you have just downloaded has gaps. And the gaps are there because the instruments are not working all the time. They're working only roughly half of the time, statistically. And also, they don't always work together. Sometimes Hanford is working, but not Livingston. Other times it's the opposite. Here, in order to create training data for coincident detection of gravitational waves, we want to train RSGW only using data from periods where both detectors were operating. So this is then creating these gaps. So wherever you see blank space, it means either only one of the detectors were working or none of them, neither of them. Okay. So, but the blue ones are exactly the time periods where both of them were working, and the segments, the data segments, are exactly the ones that are contained in this large data file. Okay. If you now look at the total duration of this, so the calendar duration is something like 180 days, but if you only sum the actual duration of all of the segments that are included here, this you can do with these functions we provide, it's actually only 82 days. So it's only a fraction of the total calendar days. Okay, now let's have a look at the first of these segments. We can use PyCBC to load it as a time series and to display it then as a time series. So first we locate the first segment. So there is a function here that automatically detects it. You don't need to look up the GPS time and write it. It will find it. And so here's what we see when we plot the first time segment. On the horizontal axis, we see the GPS time. On the vertical axis, we'll see the strain. So I assume that maybe this is not what you were expecting. Can you confirm this? Is this what you thought you would see? Let's take a poll at this point.
Let's see.
Anyone wants to comment? No guesses?
Βλέπω χεράκια.
Okay.
Χέρι, ας πούμε.
Oh, where are the hands?
There are hands.
I don't see the hands.
Not hands up, thumbs up.
Oh, okay.
That was what they were expecting.
Okay. All right. So then, good. So you were expecting to see noise and probably some large glitches, right? And this is what we see here. We do see a noise time series, but from time to time we see very large glitches happening, that we need to take care of later. But what about the vertical axis? Are these the units that you were expecting for gravitational wave data or noise data from gravitational wave detectors? Do you agree with this amplitude? Yes, no, or no answer? Okay, I guess I should reveal at this point what the answer is. Okay, so obviously these are not the right units for the strain. Otherwise, we would not be having a good time at the moment if gravitational waves were so strong. In reality, what is happening is that for the machine learning gravitational wave data challenge, the format in which these noise files are created assumes that the strain is multiplied by a certain factor. This factor is provided by PyCBC. It's called dynamic range factor. And the reason this is done is to avoid storing numbers of order 10 to the minus 20. This is the reason. By multiplying everything by this dynamic range factor, you store numbers that are on the order of 1 or 2 magnitudes from unity. And but when you want to work with this data, you need to revert. So you need to divide by this factor. And once you do this, then you get the real data. So please don't forget this fact that you need to divide by the dynamic range factor in order to have data of the right size, the strain, to be of order, including the glitches. You see one reaches 10 to the minus 18 in Hanford and 10 to the minus 19 in Livingston. If we now take only the first 2 seconds from the first data set, this is what we get. This is now far from a large glitch, and so the strain is of order 10 to the minus 20. This looks like nice oscillations, but obviously these are just noise created for different reasons in the experiment. By eye, we cannot distinguish here any real gravitational wave, not even injections that if we create injections, still there will be 2 orders of magnitude smaller than this. So initially the noise is dominated by various low frequency oscillations. And this is exactly why the whitening is absolutely necessary to balance the strain at different frequencies. This is what Alexandra mentioned earlier. Okay, so this is then what is in the noise file. So we then perform the injections. Let's see, is this concluded? Yes, all injections are done. And so now here, if we go to the directory, data 7200, we see that indeed we have created test, validation, and train datasets for the background, the foreground, and we have also files that contain information on these injections. Okay, and these will be used then for the training. So before we take a break, let's have a look at a second notebook that will allow us to see the actual injections. This notebook is also provided in the repository. You can, initially what it does, it simply loads the foreground data for training that we just created in this data 7200 repository. And it does exactly the same steps as in the previous notebook. It prints the contents. Here now we only have one data set since we have taken just 2 seconds. And we can see here the table again, the data coverage and the gaps. So this is now the continuous data for just not 2 seconds. It's actually 7,200 seconds. And the real duration is here, 0.083 days. If we go to the first time segment, it's by eye, it looks exactly the same as before because you cannot distinguish the actual injection. So nothing appears to have changed. But if we then load both the foreground data and the background data, their difference is exactly the injections that the gravitational waves that we have injected into them. So we can actually subtract the two, and then we should be able to see the injections. So this is what it's done here. We calculate simply the difference once we have loaded them. So we call these injections, and now here they are. Okay, so in these 7,200 seconds of training data that we have created, we now see several hundreds. In reality, in the data that we'll discuss after the break, we will create a different injections file where we will use each of these injections roughly 19 times because we inject it into different noise segments. So in reality, we will reach up to 10,000 injections for this minimal training. But here, for the moment, we see these several hundred of injections in this short segment of 7,200 seconds. If you zoom in into the first part, here you can now see a very nice waveforms corresponding to different choices of parameters, different masses, different spins, different orientations, or sky localization. Okay, these are randomly selected and injected in this part. And you see that they are roughly 20 to 24 seconds apart. When these are injected, they are not injected at a fixed time, but there is also some randomness in where exactly it is injected in order to allow the code to learn better. Okay, so I think, I think that this is all that we wanted to discuss for the first part. You have now seen, if we go through the repository, you have now seen exactly how to obtain how to generate the environment, how to obtain a noise file, and how to create injections into this noise file. And we have inspected what we have created with these two notebooks, and we're almost ready to start training AresGW. AresGW is written in PyTorch, so if you want to run it meaningfully fast, you should use a GPU card. In reality, it can also run on CPUs, especially if you have available 16, 32 or more CPUs. It can run on those, but it will still be slower than if you use a good GPU card. And in fact, when we say good GPU card, even a 3070, which is an 8 gigabyte card, relatively inexpensive, you can many of our production runs were done on this small card. 4080 is even better. 5090 is our newest card that we are using. So now, because these cards come out every couple of years, in the meantime, the Python environment changes, the CUDA and the PyTorch also specifications change. So basically, for each new card, you need to create a new environment. So here we provide two different environments. One that works well for the a bit older cards, 3070, 4080. If we go to the actual file, we see it uses Python 3.10, PyTorch 11.8, and works well for those cards. But for the newest 5090, we had to upgrade to Python 3.12 and PyTorch 13 actually with, PyTorch GPU 210 with CUDA 13. Okay, and this worked fine now also for the new card. So we need to create one of these environments depending on which card you have. And then you enter, conda activate, you enter this new environment. So here, now I go to the main directory, and now I activate AresGW 1590. All right, so now we are in this environment, and what can we do there? First of all, we should note that even though the initial version of AresGW, the one with which we participated in the challenge, where it was still not called AresGW, but Virgo Auth, there we used the injections provided by the organizers. Then in Model 1, and also in the newer models, we are using a different form. We have another script, waveformgen.py, with which we generate waveforms that are now stored in NumPy format. Right? So it takes the background training data that was created, and it generates a new file that contains injections for training in NumPy format and injections for validation in NumPy format. These are the ones that are actually used. The difference is, we will see it also in a tutorial, that now we have the actual waveform as a time series. And during training, the AresGW can dynamically pick a certain noise segment and inject a certain waveform and do this at every epoch. And so there is a randomization of the training process and an augmentation of the training process. Also, in the spirit of performing a learning that is curriculum based on the signal to noise ratio of each waveform. And so we don't rely on a fixed training set from the start, but we produce training segments while AresGW is training. So this is what is the flexibility of this approach. And as I said before the break, each only injected in 19 different noise segments. This helps for the network to understand that this is a waveform, and it can distinguish it better compared to noise because it has seen it embedded in different noise segments. So even though we start with 267 different injections, multiply this by 19 times, you reach almost 10,000 training data segments, basically 5,000 injections plus 5,000 noise segments. So let's try this here. Okay, and so here you see this script generating 267 waveforms. It runs relatively fast. So we can wait for this. Okay, it's done twice, once for the training and once for validation, because we want to have completely independent sets. Okay, if we now look at generate data, okay, so here is the NumPy file for injection for the validation process and the corresponding one for the training process. So we have produced the files. These are smaller than the previous ones because now they refer to a smaller number of waveforms, even though they contain the full waveform. We can inspect what we have generated using this file here. This is a notebook inspect injections file. So we specify, for example, we can see what is contained in the injections train file. We load it. If we inspect the data structure, at the root level, it has a lot of information. Yeah, in fact, okay. In fact, here we first inspect the HDF files that we produced before the break, and then we're going to also to inspect the files that we just generated. So let's first have a look at the HDF files that we produced before the break. Here, these do not contain the full waveforms, but they contain the full specification for generating these waveforms. So you see here the root keys: chirp distance, coalescence phase, declination, distance, inclination, mass 1, mass 2, chirp, polarization, and so on. So all these different parameters completely specify a single waveform. The approximant used is the IMR Phenom XPHM that has free spins and also includes precession. It has a lower frequency cut at 20 Hertz. And yeah, this is the main information. And so we can now print the tree and see what is included in this HDF file. It has, for each of these parameters that determine a waveform. It has a dataset, which is these 583,000 different possible combinations that produce different waveforms. So these HDF files, they are large because they include all these nearly 600,000 possible waveforms that you could use. You can, of course, create an even larger one, but this we found was sufficient for our purpose so far. So if you then look at the histogram of each of these parameters, you can see that how the chirp distance scales, because we use a uniform distribution in chirp distance square. The coalescence phase is uniform. The declination, the distance, chirp mass, the different masses, inclinations. According to how Alexandra described in the first part, how this training dataset is produced, these are exactly the distributions of these parameters. And if you want to inspect individual waveforms, now you can open the file that we just created, which is the NumPy file. And in there, you see the actual waveforms that are created and stored. Here are a few such examples where you see the waveform both at Hanford and Livingston detector. And in this file, we have 267 different such examples that we then inject each one 19 times. Okay? So, our training data are ready, and we inspected them, and then now all we need to do is to start the actual training of AresGW. This is the command that we can run, and in fact, we will run it now. We will see how it goes, but then Alexandra will take over in a short bit and explain the different parameters, what they are, what are the good values, and how you can obtain them, or how you can experiment with such values. Okay, but let's do some first training. Okay. We want this one, yes, okay. We go to the root. Okay, let's see. Haha. Of course, we have not entered the environment. Okay, so let's go now to, wait, I was in the different, here I was. Okay, here we are in the environment. And here we are in the, okay, good. Here it goes. So AresGW is running on GPU, and you see here it is at epoch 0, already done. It goes to a second epoch. In total, it will run for 15 epochs. For such a minimal example, this is sufficient, but even for the production runs, this is the number of more or less epochs that we use. Also, you see that at each epoch, it runs once for the training and once for the validation. For the training, it makes 322 steps. This number comes out because if you consider the number of training samples that you have, so 267 times 19, and divide by the batch size, which is 32, that gives you 322 steps that you need to do to complete a full epoch. So full epoch meaning that the code has seen all the data once. And then you do a back propagation, and then you do a second epoch, and back and forth. 15 times back and forth. The weights you hope will adjust to values that allow you to perform an accurate classification between noise and gravitational waves. So at the moment we are epoch 5. Okay, this will take some time. We will come back when it finishes. Let it run. It only takes a total of 12 minutes on this card, this minimal example. Otherwise, if you do the full training data that contains hundreds of thousands of waveforms, it will take you less than 2 days. All right. So, yeah, we have this information here about the steps that you see. When the training finishes, the weights of the model are stored in the directory that we specify here, in this directory, and in a file called weights.pt. Okay, then you can run the code. Actually, we have two separate files, one for training and a separate for testing. With a test.py file, you can load the weights of the trained model, and then you can apply this model on your test data to produce your triggers, to try to find gravitational waves. Okay, so we will run it on the foreground test data, but we will also run it on the background test data where we have not done any injections. We do this because since this is a controlled experiment with the injections, we know where we have injected. We know the answer, we know the ground truth, so then we can evaluate the outcome and make a statement about how sensitive this code is, how good it is in classifying gravitational waves compared to pure noise. So then Alexandra will talk about how to apply this to real data that you can download from GVOSC in order to search for actual gravitational wave astrophysical events that were recorded by the LIGO detectors. But for now, we are still at this controlled experiment, right? So,
maybe I can
in fact,
the arguments.
I just need to actually, to discuss two more things, and then you can take over and discuss the arguments and continue. Huh?
Okay, so you will firstly show the notebooks, and then I will speak about the arguments.
Yeah.
Okay.
Do you prefer now? We can go. Yeah. Okay, go ahead. While this is still training. Okay.
It's fine, we can do it that way. There is a question in the chat.
Okay.
Regarding the steps you just mentioned.
Why do we calculate the number of steps with this formula? Is it good practice we should use in general? Well, it all depends on the number of data samples that you have for training and on the batch size you choose, which is an important hyperparameter. If you use a batch size of 1 only, it would mean that here it would have to take 10,000 individual steps, and at each step it will try to adjust the weights. So it will see one sample and then adjust the weights of the whole network according to that one sample. But this is not a good practice. You also don't want to give the whole data set at once and only then adjust the weights. somewhere in between is the best, the optimal value. So this is a matter of trial and error. So you use different batch sizes, and based on the outcome, you decide which one is optimal for your specific training. Here, we have tried with 8, with 16, 32, 64, and so on, and 32 appears to give the best training, and that's why you get this number of steps. Okay, in fact, the training is done. Training is done, and you see that it actually took only 5 minutes.
Okay.
Yeah, it took only 5 minutes on this minimal example. There are now in the printout an overall accuracy of 57%, not at all impressive. For the positives, it looks a bit better, 66%. For the negatives, 48%. But keep in mind, this is only a minimal example with only 267 different waveforms that have been injected 19 times each. Not more than this. So for me, it is impressive that it can still reach such accuracies, even though it has seen very, very few samples. So, Alexandra, what are these parameters now?
Okay. Should we switch the mics?
Yeah.
Perfect. Maybe you should close the share because before I did some. Okay. Can you see my screen?
Yes.
Can you hear me?
Yes, yes.
Can they?
I assume. Go ahead.
Okay. So let's check the different arguments that we have, starting from some general command line argument, such as the output dir. The output dir corresponds to the output directory, and we can give the name that we want, and even if that directory doesn't exist, the code will automatically create that specific output file. However, we need to know that if you don't specify an output directory, then the argument output dir will be none, and then that will raise a type error. So you need to specify a directory, even if you didn't create it. And we basically have the same for the data directory. The data in which we will have inside the background file, the foreground file, the injection file. So again, you need to specify where those data came from. Otherwise, it will also raise an error. Now, going to the actual training command line arguments. So one of those arguments is the slice dur, which corresponds to the slice duration. So what does this specific argument do? We are basically taking original slices of length equal to the slice dur parameter second, and then we use those to calculate the power spectral density we use in order to make the whitening. And then finally, we do extra crops and we end up with 1 second segment. So the input in the network will be in a duration of 1 second, but we did use a complete of, for example, if we do keep the default of 3.25 seconds. And why do we need it? Why don't we use just 1 second and perform the whitening there? Because we do need longer slices in order to calculate a good power spectral density estimation. And as I mentioned, we use that in order to perform the whitening, which also involves dividing the frequency domain data by the square root of the estimated PSD. So if the segment is too short, the PSD estimate will become very noisy, and that will actually give us a poor frequency resolution. So that is the reason we need a larger segment. And also after the whitening, we need to do the extra cropping because, as I also mentioned before, when you do the whitening, you might have artifacts in the edges of the segment. So that is why we end up keeping only that 1 second. And as to why specifically 1 second, why don't we take a larger PSD in order to have a larger input in the file? That depends on the chirp mass ranges that you actually work with. For the mass ranges that we work in that specific code from with masses from 7 solar masses to 50 solar masses for the individual masses, 1 second is perfectly fine. If we want to go to higher masses, we can actually reduce the time. And if we want to train with larger masses, we will need to actually raise that time. Another argument is this slice stride. And what does that specific parameter do? Well, the code, as I mentioned before, computes the PSD over a sliding window of slice duration seconds. And this longer window is then used exclusively for estimated local noise statistic. And that visually looks like this. But then our code creates positive samples during its training. So, for example, in order to create that positive sample, we need in that specific region, let's say that we did use the default slice stride duration, an injection needs to be performed, and we do that at a random quarter segment of 1.25 seconds in duration, which is then whitened using the same PSD computed for the full 3.25 window. So yes, basically what is happening here is that the 3.25 seconds of PSD window itself slides forward with the stride of slice stride seconds. So for example, here you see this, then if we do keep the default duration, we slide that by 2 seconds, then another, then another. So anywhere within here. And now moving forward, we also have the resum from, and that specific parameter, if it's not known, give us the opportunity to load weights into the model, not use some random weights, for example, at the first epoch, but use some different weights that we might have from another training or something like that. So did it pass something? Oh, that is what's happening. Let me. Okay. Perfect. Now, what is important to note here? Let's say that I did actually save the weights from the training in an epoch in the middle, for example, the fourth epoch. If I do use those weights in a new training, it's not exactly like I'm starting the full training session from that specific part, because we do use the same weights, but we don't also save the optimizer state, the scheduler state, the warm-up state, and all the other things that we actually calculate in the different epochs. So therefore, that specific argument should be treated as weight initialization from a checkpoint rather than a full training session resume. Now, one very important parameter in general when we talk about neural networks and machine learning is the learning rate. Here you see also the default value. And what does this specific parameter do? Well, it is a key hyperparameter that controls how much the model's parameters are updating during the training in order to reduce the loss function. So basically, what does it do? It helps adjusting the weight so that the loss function is reduced. So it does determine the size of the steps that the optimizer will take. Typical values are small. For example, you can see here 10 in the power of minus 5. And there are a lot of reasons why we prefer small values. For example, a high learning rate can make training faster, but that may cause the model to overshoot the optimal solution. For example, you can see here, our goal is to reduce the loss function, so being the minima here, but because we do use a big learning rate, that ends up going far away from that. While if we did use a smaller learning rate, we would go smoothly to the minimum. And here I also mention when we are basically using it, we use it to set the Adam optimizer learning rate. So it also directly controls, interacts with the warm-up, and we will mention what warm-up is later on, and also multi-step learning rate, which also includes two other arguments that we will see later on, the milestones and the gamma. So let's start with what are the learning rate milestones. So what does this parameter do? Basically, we use it here, and at the end of each epoch, if the epoch count has passed that specific milestone, for example, here we did set that the milestones at the default value are the epoch 20 and the epoch 50, for example, then the multi-step learning rate will be multiplied by gamma. So what does this mean? What is exactly happening here? Basically, that specific argument defines specific epochs at which the learning rate will be reduced during the training. And this is a part of a learning rate schedule, which is a common technique which is used to improve coverage in neural networks. Basically, during the early stages of the training, we might need a larger learning rate, which will help the optimizer actually explore a bigger part of the parameter space quickly and make large updates to the model weights. However, in practice, I need to know here that in practice, we sometimes start with a smaller learning rate in a first epoch, and then we finally end up with a big learning rate. However, once this phase is complete, we do need a larger learning rate, as I mentioned before, in order to be able to move efficiently through the parameter space. So as the training progresses and the model approaches a good solution, those large updates maybe end up making the optimizer again overshoot or oscillate around the optimal. So for example, in this here, if we're now very close, for example, we are here and we are very close to the solution, if I keep having large learning rate steps, then I might end up going around that solution. So for that specific reason, we do use the milestones in order to, in those epochs, reduce the learning rate. And how do we reduce it? Well, we have gamma, for example, which is used in the multi-step learning rate here. And at each milestone, the learning rate is then will then be updated by learning rate multiplied by gamma. So, for example, we have the default value 0.5. So if we do the multiplication, we will have in milestone 20 half the learning rate that we had in milestone in the previous epoch, which was the 19th epoch. And since we're talking about epochs, what does that specific argument do? Well, basically, the more epochs we have, the more passes we have through the training loader, just like Professor Stergioulas mentioned before. And why do we need it? Well, again, it's a complete pass of the training algorithm of the entire training dataset. And during each epoch, the model processes all available training samples, which are typically in smaller batches, again, as Professor Stergioulas mentioned, and we will see also later on because that is an argument as well. So because neural networks start with randomized initial weights, a single pass through the data is usually not efficient for a model to learn meaningful patterns. You can think it as you would study for a test. You don't just read the whole all the nodes. You're just taking parts, and you learn that part, and then you go to the other part, and then you go to the other part. This is basically what the neural network does. So multiple epochs are therefore needed to progressively refine the model. Early epochs allow the network to learn coarse patterns in the data, while later epochs help fine-tune the weights and reduce the training loss further. Okay, however, we need to note, we need a lot of epochs, but we need to be careful to not have too many epochs, because that can actually lead to overfitting, which is when the model starts to memorizing the training data instead of learning generalizable features. So we need to find a sweet spot. Now, for the curriculum learning, the SNR schedule that you can see here, what does it do? Well, what it happens here, as I also mentioned in the presentation before, is that not all the epochs, the network doesn't see all the injections in all the epochs. Which signal to noise ratio injection samples are used during training change over the different epochs. And this argument expects that specific format, in which, for example, here, what we have in the default means that in the first 5 epochs, we will only include injections with SNR from 15 to 100, while in the next 5 epochs, we will include the injections with SNR from 1 to 100. I also need to point out here, because we mentioned the SNR, that those SNR values that are referred here are not computed in the standard way we compute the SNR for each injection. Instead, we are estimating those using an empirical expression that depends only on the chirp mass, the distance, and the inclination angle. And you can see the formula in our paper here. However, since I have the plot here, you can actually see that the real SNR of the injection, the optimal SNR, which is depicted in blue, is very close to the values that the empirical formula gives, which is here depicted with orange. And okay, you might ask me, why do we complicate things? Why do we need that? Well, curriculum learning adjust the difficulty of the training data by controlling the signal-to-noise ratio at different stages of training. And that helps because, for example, if we use the approach of starting with the higher SNR signals, which are more clear for the network to see, we actually help the network to adjust its weights in the first epochs. And then when we give signals that are more difficult for the network to see, it already has some good weights in order to try to find things there in order to understand that there is a gravitational wave in there. So our recommendation is to start with higher SNR signals and then proceed to give lower SNR signals. You can try whatever you want, however. In our model, Model 1 and Model 2, first we expose the network to simpler examples before introduce the more challenging cases. Now, the batch size. I won't go into the details here because Professor Stergioulas actually said everything that I wanted to say. Again, the batch size determines how many training samples are processed together in a single forward and backward pass. And it is important to find again a sweet spot because too small of a learning rate of a batch size won't really help the training, and the full data also won't help the training. In one case, you can't really find patterns to generalize it with, and in the other case, you actually have all the data, and because those networks are actually very powerful, they end up just memorizing the training data, and then they can't really generalize well. Now, going to the warm-up epochs, what does that parameter do? This argument controls whether a learning rate warm-up phase is applied at the beginning of the training. If warm-up epochs is greater than 0, then the learning rate is gradually increased from a very small value to the target learning rate that we gave as a learning rate parameter. Here you can see how it is used in the code, and you can see what each of those things inside mean. Basically, what we do if we, for example, have 2 warm-up epochs is that we start from a very, very small learning rate, and then we end up through the 2 epochs with the learning rate that we have. So at the end of the second epoch, if we decided that we want warm-up epochs at 2, we will have the learning rate that we wanted. So that way we can stabilize the weight in the first 2 epochs, and then we give a large enough learning rate in order to be able to also explore the parameter space. So that is a training strategy. You can choose to use it or not to use it. It seems that for RSGW Model 1, that helped. Okay. Yes. Now, clip norm. This is another argument that has to do with exploding gradients. Basically, what we do is that we set a maximum allowed norm. The norm refers to the magnitude of the gradient vector of the gradients during the training. And after the gradients are computed through the back propagation, they are clipped using this. And that means that if the total gradient norm exceeds that specified value, which the default value is 100, then the gradients are scaled down so that the norm equals to the defined threshold. And we need it because that gradient clipping is used to prevent exploding gradients, which is a phenomenon where the gradient values become extremely large during training, and that creates unstable updates to the model and might also lead to numerical instability or divergence of the training process. Now, another parameters that we did discuss a little bit before, because we had a question about it, is the p-augment. That parameter controls the probability of applying a specific data augmentation procedure during training. And with probability equal to p-augment, the noise segment of the Livingston detector is replaced with another randomly selected noise segment. So we don't have the correct, the same segment that actually was for the Livingston detector and the Hanford detector at the same time, but another time segment for the Livingston detector and another for the Hanford detector. And that is implemented in the slicer dataset SNR if you want to check a little bit more what is happening. Now, why do we need it? Because dataset augmentation helps us improve the robustness and generalization ability of the network. By randomly replacing those noise segments, the model is then exposed to a wider variety of background noise conditions during the training, and that prevents the overfitting and also enables the network to see basically more noise of the same form. And the last 2 arguments, the one is simply the training device, and that actually just says where we want to train, if we want to use the CPU or the GPU as our device. As Professor Stergioulas mentioned, GPU is a little bit faster, so it may be a better practice if you have a GPU to use a GPU. And the other parameter is the number of workers, which specifies how many parallel worker processes are used by PyTorch in the data loader to load and prepare the training. So each worker process loads and pre-processes data independently, allowing multiple batches to be prepared simultaneously. So those are all the parameters in the training. This PDF is also uploaded on the Git, so you can find it. And if you have any questions, please do ask.
Actually, there is already a question in the chat.
Perfect. Yes, let me see. Okay. So, okay, that wasn't necessary. No, that was the previous one. For each phase of curriculum learning, if we have 10 signals with high SNR, Yes, basically, generally, when you train a neural network, you want to have a balance. So you don't want to give, for example, 10,000 noise segments and only 5 segments of positive samples. So you want to have a balance. So if you have, for example, 10 signals, it is good practice to also have 10 background segments in order to calculate the weights. I hope that answers the question. I don't know if Professor Stergioulas wants to add something, but basically that is what's happening.
Yeah. Okay, if there are no other questions about this part, we can continue with some evaluations here.
Okay, so you want to try, you want to open the mic?
Yeah. Okay, so now I'm sharing my screen. This is where we stopped a few minutes ago. We reached the finish line of training for this minimal model of very few injections. And what we can check after the training has finished is to go into the directory where we store the weights, because there we also get a plot. And this plot shows you the loss and the accuracy as calculated by PyTorch for this model during training for each epoch. The blue line corresponds to the training dataset, and the orange line corresponds to the validation dataset. Now, if we look at the accuracy, this may look very puzzling, because we see that the accuracy in the training data initially is quite high, and then it drops, whereas in the validation data, it starts low, and then it saturates at a certain level. So how is this all explained? It's explained exactly because of the curriculum learning, because in the first few epochs, we let the code learn only the strongest injections, which are easy to learn. So it is performing well, and it in the training phase, in actually reducing the loss function. But this also has an imprint on the validation set, because there indeed you have a rapid increase in the accuracy because it learns these strong signals. Then gradually we allow the code to see weaker signals, and later the whole data set. And there are basically small improvements after that, because we have this very minimal example of very few number of waveforms overall. In the full training with hundreds of thousands of examples, you would see a different improvement. In the later epochs, you can see the actual curves if you go to our publications. These publications actually are here at the end of the repository. There is a link. In fact, here, refer to the AresGW publications. This should open a library in ADS with all publications where AresGW and its previous version, Virgo Auth, has been used. And basically, this is the main publication where you will see the actual plot for the full training dataset. But here we have this minimal example, but still you can interpret what is going on. Okay, and also what you can do is after training, to look at the outcome, load the triggers. So load the results in the file results test foreground events. The code is storing all the triggers it finds with their time and the ranking statistic that it assigns to in this classification scheme. And the same for the background file. So you can load both of them and then plot a histogram. This is the histogram. For this minimal example, because we have very few data, it looks a bit strange. In reality, if we had a large data set, we should have more and more counts as we go to smaller ranking statistic. Here we see a maximum around 0.8. If, however, you use our logarithmic ranking statistic, right? Because what we have determined in these papers is that the actual astrophysical events are all present at a ranking statistic larger than 0.9999. So everything you see here practically, except for a fraction in the last bar, everything else is noise, right? So in order to separate the signals better from the noise, we have defined a logarithmic ranking statistic. This is the definition. So we now convert to that logarithmic ranking statistic. And so the same data plotted versus this ranking statistic, which we call RS, looks like this. So now the very few foreground signals, these blue bars, these contain signals that triggers that were identified in the foreground that were not there in the background. So in a realistic scenario, this would correspond then to real gravitational waves. Everything else is noise. And so the exact properties, if you use a very large data set, actually conform to a Poisson distribution. This is something that we can easily confirm. But for actual signals, you need to go to a very high RS. And it terminates at 16 because this is basically what we enforce in order to avoid rounding errors due to double precision. Okay, and the last step, before then Alexandra talks about the application to real gravitational wave data, is this last utility, evaluate.py, which we have which we also provide here. It is from the challenge repository. And here this imports the injections and the triggers that are produced for the foreground and the background. And what it does, it calculates the false alarm rate as a function of a ranking statistic and the sensitive distance as a function of a ranking statistic, and it then produces the corresponding plot. So you run both of these lines, and you get here, this is done directly inside this tutorial notebook, and you get this plot. Okay, so false sensitive distance in megaparsec versus false alarm rate as a function of 1 per month. So what we see is that if you allow a very high false alarm rate, then theoretically you reach a high sensitive distance of several thousand megaparsecs. But in practice, we want a false alarm rate that is better than a few per year, or maybe a few tenths per year in the worst case, depending also on the astrophysical probability that we calculate. But the strong signals have false alarm rate better than twice per year. So to reach such small false alarm rates, you need to have a corresponding long data set. You need to have a data set of several months that you evaluate. Here, with a data set of less than 1 day, you cannot reach to smaller false alarm rates. So here the curve collapses at quite high false alarm. But it's only for demonstration how to run the code. Don't take this curve seriously. You need to download the full dataset, do the full training, apply to the full LVK data, and construct the actual curve that corresponds to the one that we have in the published papers. But at least the low part still more or less it agrees, the low part. It's just at the high false alarm rate part. You still get it, even with this Millman example.
I will show an example.
Yeah, but how it continues, you need more and more data and longer running times to reach smaller false alarm rates. Okay, so that's it from me. And Alexandra now can continue with the last part, which is about evaluating real LVK data using AresGW.
And tested. Perfect. So, okay, well, first of all, we will see how we can use test sets in order to actually do an evaluation using some very commonly used sensitivity metrics, such as the sensitive distance and the number of detected injections. Basically, the work we did in the last paper that I also showed in the presentation. Now, due to time constraints, I won't go into the detail on the notebook because the notebook is about 900 lines long.
Can you increase the font size here?
Yes, of course I can. And I can also that like this. Okay, but the beautiful thing about this notebook is that basically every different thing that we do is actually referring to a different function in that notebook. Even the plots that are created in different functions. So I also have a lot of comments here in order to help you understand what is happening and why it's happening. However, if you do have additional questions after the hands-on session, because as I mentioned before, I can't really go into detail to the code, don't hesitate to actually send an email with your questions. So,
in reality, I will mention about the ticketing system in ACME, where users can send questions directly there. And so
yes, correctly. Yes,
we'll mention this at the end.
Perfect. Okay, so as I mentioned before, here we will do basically an injection study using two different test sets of a duration of 1 month. Those data sets that are used here are some of the data sets that were used in that specific publication, the one here. So this specific notebook is uploaded in the Git repository. This one is in another file. It's not, no, it's here. So you can't find this, but because the files that we use here, because we use the foreground file, the background file, the injection files, and then the evaluation files, because those are very big files, 20 giga each, I think, if I remember correctly, we couldn't upload them. So you would need to actually follow the instructions we give in here in order to obtain and run the same exact thing that I will run right now. So first of all, we have obviously our inputs. As I mentioned before, we do need the HDF files, the injection file and the foreground and background outputs. And we also do need that file here, that Python file here, that contains also two additional functions in it. The function find injection times, which basically searches which foreground segments do contain real injections in them by checking the time of coalescence that is included in the injection file, and also find the closest index, because we will also need the index in order to be able to carry on with all the lists that we have in that specific notebook. Now, we do have the duration used here. All those files, as I mentioned before, is in 1 month duration, so 30 days in total. I also here use those two classes just in order to be able to froze that specific configuration and not have problems later on if you change something, for example, in the notebook. All those stay the same. Here we load the paths for the different files that we will use, and here we basically have those parameters just in order to be able to use in the file names, because they all have the same exact format. This specific parameter here, you will see, we will discuss about different plots. One of the plots will show the number of detected injection versus the false alarm rate for both the test files that we will check here. And here we decide in which false alarm rate we want to see the number of detected injections with the CIRPMAS. That will make sense later on, but I want to go as the notebook proceeds. So, okay, we set up our plot style. We create the directory if it's missing. Here we see where we can obtain our files, and we also now load the event times here. Now, what do I mean I load the event times here? Remember before that I said that in the files that are used in that paper and in the challenge paper, there are still 37 gravitational wave events in them, because in the challenge only the events from the catalog GWTC2 were removed. So we have here a file, a CSV file, which is included here, that is also uploaded, which includes, it mentions which was the time of the event before, the actual time of the event, and where that event shifted, because we have different background segments, so we have a shift between the two detectors in order to create different background. So in order to be able to remove those events, you need to be able to know where they shifted. So here for those files that have different injections but the same background, you can use that one file and you can find where the events did shifted. So here we do load that specific file. This is what we see here. And then we read the injection parameters, which we'll use because, as I mentioned before, in order, for example, to create the sensitive distance, we would need the chirp distance, and we also will find the CIRPMAS in here. Here we do read the files. The HDF files basically show the ranking statistic of each trigger and the time that we saw that specific ranking statistic. And we also have one more parameter, which is the time variance, the tolerance, which is for all equal to 0.5. That is just used in that specific notebook. It would be just one value. But yes, Now, here I also have one more function that what that specific function does is that if we actually have the event list, if we decide that we do want to remove those gravitational wave events that are remaining in the data from our background events, what we do is that we go to that specific times of those events and then we set their ranking statistic equal to 0. And because we consider positive samples, triggers that have a rank statistic greater than 0.5, that basically says, okay, that specific trigger is actually noise. And that way, those events do not bias our false alarm estimation later on. You can see a lot of things regarding all those things that we're discussing for that specific notebook in the corresponding publication. Okay, here we compute the false alarms. Yes. And the first plot we will see here is the plot of the time difference. What do I mean by that? Let's go, for example, to that specific test. We have two tests, one that had a seed 32 and one that had a seed 12,019. And what we plot here is the time difference between the injection and the trigger time that the network gave. And we see here that for the number, the false alarm equal to 1 per month, 10 per month, and 100 per month, basically most of the triggers, most of the injections detected within that specific window between 0 and 0.18, you could say. Probably the trigger that you see outside of the 0.3, for example, those are probably background noise and not actually injections. I mean, the network didn't see the injection and produced that rank statistic. It just happened that the injection is near. And I say that because we have a clustering every 0.35 seconds. So that is out of the clustering. So this is the first plot. We have two for the two tests that we are checking, but you can actually have more tests. The code is set up in a way you can use as much tests as you want. Moving forward, I think I saw there is a question. No, I saw a message.
Writes in line 114.
114, yes.
He gets an error because of the directory.
Yes, that is not uploaded in the GitLab because those files are very big. So this is the only notebook that is uploaded with everything you need, but the files. So you would need to create those files or maybe smaller files and run the specific notebook. You won't be able to run it right now, sadly. They are very, very big files. Okay. So this is what that specific function is doing. Then we will create plot for the injection count versus the chirp mass, again by the false alarms. And again, you can see here how that is actually happening. It's a pretty straightforward plot. And we end up with those plots for the two different seeds that we have, the two different test sets. And you can see here that we have obviously less detections with false alarm equal to 1 per month, then more for false alarm equal to 100 per month, and finally even more for 100 per month. And you can also see that basically the distribution between the two sets isn't that different. So the detectability of the network basically remains stable when we have the same background. I mentioned before, we have the same background in those files, but different injections. So we can actually have the conclusion that, okay, the network is actually robust in the injections, if the injections have, of course, the same distribution as the training, or a similar one. Okay, and we also have a sensitive distance plot, which is the plot that Professor Stergioulas showed you, but that he showed you actually had very little data in them. But here we have plenty of data. We have 1 month of data, so we can actually create the total plot. And here is the false alarm equal to 1 per month. You can see the difference between those two different test sets is actually small. For false alarm, for example, for 1 per month. One additional plot that's happening directly below that plot here is the plot for false alarm equal to 1 per month that we did set in the beginning of the notebook, and it provides this plot. So here we can see the difference between those two sheets. Specifically in that case, you don't see much of a difference, and you don't see much of a difference between the two because, again, we have the same background. If we had a different background, you would be able to see a much bigger difference between the two because there is a very big variance for the number of detected injection versus the chirp mass at lower false alarms, at lower false alarm rate. So, yes. Basically, that's it for here. But what we saw, the plot that I just showed you, refers to when we do still leave the events inside. I hadn't removed those events. If I want to remove them, I can go to main here and set the remove events from false to true. And if I do that and run again, it will create different plots this time. So, for example, you will see those numbers will actually increase very much because the events actually bias a lot the false alarm calculation. So, give it a minute. It is very quick, actually. So, see from 2,000 and something, it went to 3 and something. It will, you will see the same here as well. And what I want to show you, because those are actually printed differently, is what happens with the plots, the one near the other. So, for example, now we had this specific plot when we had the events still inside the data. And we have this plot when we remove the events. You see similar distribution, but if you check axis Psi, you will see that there is a difference here. Because when we remove the events, the false alarm rate changes and we have much more detection. So it is very important when you try to do comparison between pipelines or for your own pipeline to remove those events, especially if you want to use the number of detected injections. If you want to use the sensitive distance, as you can see here, because I also have those plots printed differently, you will see that the difference is very small. So sensitive distance is actually pretty robust. So that is for this specific notebook. Before going and end with the real data, which is a very small analysis, are there any questions? Can you see, are there questions in the chat?
No.
Okay. Anyone? If you want to raise your hand or ask in the chat.
Looking at the time.
The other is very small.
5 minutes, because then I also need to...
I don't need more. It's very small, the other one.
Mention something about the ticketing system and the questionnaire. We will close around 5 to the hour. Okay.
Okay, so let's go to the other. The other notebook that I'm using is this one, AresGW Model 103 Data M2. And that specific notebook you can run. You have the only file you need is that, and you can run it right now, for example, if you have the repository cloned. So what we did here is basically we did run AresGW Model 1 on the second month of 03. So that file contains the evaluation of AresGW Model 1 in that specific month. And here I do mention briefly everything that, again, Professor Stergioulas said about the ranking statistic, that we do use the logarithmic ranking statistic in order to be able to visualize our results better. And if you want more about that, you can actually go to this publication and see what is happening. So we do load our data. We extract those specific parameters, the rank statistic, the time, and the var. We don't use the var anywhere within the notebook, but you can actually load it. I also plot here the first trigger time just to be able to see the GPS times that we're working with. And here I do include the merger times of the events that are included in the second month of O3A. And here you can see the GPS time. And here you can see their names and the catalog that they are in. Here in that specific month, it happened that there are only events from the GWTC catalogs and AresGW Model 2. However, there are also the IAS and OGC catalogs. They just don't have events in that specific month. So what we do here is we plot the time array and the stat array. And now we can clearly see those two are events. By the way, you will see that later on. How the noise looks like when we plot it like that. And there are some triggers that surpass the rest of the noise. And those are probably events. And yes, we will see that later on. They are actually events. We can also plot the histogram, and now that we have 1 month of data, we can see the same that, again, Professor Stergioulas showed before, that we have all the noise here and we have some triggers that exceed that noise, and those are probably gravitational wave events. And here I also plot for each event. You can see the dashed red line corresponds to the event, and you can see the ranking statistic of the event and the ranking statistic of the noise around the event. For example, this is much louder than the noise around it. Same here, this is lower. And you might see sometimes some glitches around, for example, that they might have larger values, but that is not happening here. And finally, you can also see the total number of triggers for a specific rank statistic threshold. Usually, at least for the AresGW Model 2 code, we would need values greater than around 4 in order to be able to have an astrophysical probability greater than 0.5. But here you can see how many triggers there are for each different threshold. And you can also print the ranking statistic of the specific events. And you can see that most of them have a rank statistic greater than 3.9, for example. Those with 16 have actually the maximum value. So they would probably give an astrophysical probability equal to 1. So that's all. If there are any questions regarding that specific notebook, if anyone ran it and want to point out something.
Okay. So we actually managed to reach the end and show everything that we prepared, and we are on time. We have a few minutes left. In these few minutes, I would like to point out, let me check here.
You want to change the mic?
Yeah, I have already my mic here.
Oh, so they hear us both. Fine.
Okay. So now what I want to share is this page in the ACME website. If I will put this in the chat also. So you would do us a big favor if you would spend a few minutes of your time to answer a few questions. Here you can select the specific training session that you participated today, and also from where you are, your career stage, and optionally your gender, and then write some feedback about how useful this training session was for you.
Can I do that?
So this will really help ACME to receive this feedback, because we have 2.5 years ahead of us. We will organize many more training sessions. So any comments would really help us improve future training sessions. Either good comments or comments about things we could do better. So everything will be useful. Also, if you experiment yourself with the code and the notebooks that we provided to you today, and you find some things that you like to discuss, there is this ACME ticketing platform. There is the link here. I will also share this in the chat. Here you can log in and you can actually write your question, describe it, write the topic, and then it will be assigned to one of us. If it is about gravitational waves and more specifically about RSGW, we will be alerted by email in order to log in and to answer the questions that we have. So please use this. This was created specifically for ACME in order to allow users to have responses quickly to such questions. So and to continue to have a relation even after the end of the training sessions, which is important for ACME and for your work too. So, are there any comments or other questions before we close?
Now is the time.
No. There was a question in the first part about the upcoming training sessions from ACME. I can share here also this page. So the next one will be in 1 week about Bilby. There will be about code regarding neutrino detections on March 16. Then virtual observatory tools for multi-messenger astronomy, March 17. Then also about multi-messenger, cosmic ray modeling,
Yes, those are
CRISP, PRINCE, and here the GWOSC tutorial. This will be very useful for those who are interested in gravitational waves, as well as GWFISH is very useful. I think they had it also before, right? It's now a second time, if
maybe
May 4th. And May 8th and 20. There are two training sessions organized by our group. One about galactic binaries for LISA. It will be Nick Karnesis who will be showing this, and probably with collaborators also. And the last one, May 20, it will be about rotating neutron star, the RNS code, and universal relations by Grigoris Papigiotis and myself. So we hope to see you again in one of the next hands-on training sessions in the near future. Then there will be many more after summer again. So this is the schedule for the next few months, but many more will be scheduled throughout the next 2 years.
there is a question if there will be a certificate of participation.
Well, we will ask the main ACME principal investigators about this, and if we are able to issue one, we will send it to you. Yes. Good. All right. So that's it. Thank you so much for attending. Enjoy the rest of the day, and we hope to see you again.
Thank you very much.
Bye.
Thank you.